Hello and welcome back to Unit 3. In this unit we're going to begin, or in this part of this unit, we're going to begin looking at 2D projectile motion. And we're going to start by thinking about what does this path look like. If you click that link, it opens this simulation. And then if you run the simulation, it opens in HTML5. And what we have is we have a cannon, a target, a statue, and all sorts of things we can control over here. I'm going to begin by just moving this guy downward and then tilting it upward. And what you see is the path of the projectile is a parabola. Okay. Now, I do need to say that right now we are ignoring air resistance. If we put air resistance on, we can see that the path is vaguely parabolic, but it doesn't go as high, nor does the projectile go as far. Okay. For this unit, we are going to be assuming that we can ignore air resistance and therefore not need to worry about it. Later in this part, we have a video that shows the effect of air resistance and what happens if you can actually remove it when objects are dropping. I'm now going to fire the cannon at 45 degrees. I also want to lower it down just a little bit so that I'm firing from the exact same height as the ground. And we see that our projectile goes and it hits the ground. Now, if I adjust the cannon angle upward and fire, we see that the projectile does not go as far, but it does go higher. On the other hand, if I adjust the angle downward, it doesn't go as high, nor does it go as far as the 45-degree angle. But if we look, the last two angles we fired at hit the exact same spot. And that's because those angles were symmetric about 45 degrees. The upper one was at 60 degrees, the lower one here is at 30 degrees. In the part 5, I believe, of this unit, we do an example where we show mathematically how those two angles are calculated. Returning to the PowerPoint presentation, we're now working in 2 dimensions. So if you remember what we had way back when in part 1, we had r equaled xi hat plus y j hat plus z k hat. Typically here, the 2 dimensions we're going to be working with are x and y, so we will ignore this. And because our acceleration is only in one direction, there is no connection between the horizontal motion and the vertical motion. That allows us to work with them sort of independently of each other. And it allows me to write out my constant acceleration equations in both directions. Notice that I'm having to put the subscripts that I dropped in the last unit back in here because I am working in 2 dimensions. Vertically, I have the exact same equations with all the x's replaced with y's. Now, since we're ignoring air resistance, that tells us that our horizontal acceleration is 0. So that removes this term, and this term from the equations. These bottom two tell us the same information, that our horizontal velocity is now constant because we have no acceleration in that direction. So really, we are left with one equation out of our possible 3 in the horizontal direction. No such simplification happens vertically. My grocery list now has 2 pieces to it. I have the horizontal piece, and even though I don't really need it, I keep the horizontal acceleration in the list just as a reminder to myself. Okay. Notice time is in both the horizontal and vertical dimensions, which makes sense because the ball is, or projectile is moving both horizontally and vertically at the exact same time. Okay. Typically, I stick time under my horizontal grocery list at the bottom of the X's, mainly because that's the one that I write first. It can go wherever makes you happiest. Okay. So we have our 4 equations for 2-dimensional projectile motion. When are these equations valid? You need constant acceleration. So that means you need to be near to the ground or near the surface of the earth. This allows the vertical acceleration to become the acceleration due to gravity downward. We also have to neglect air resistance. As soon as we put air resistance in, as we saw in the simulation, it doesn't go as high vertically and it doesn't go as far horizontally. And the air resistance would actually couple the 2 motions together, the horizontal and vertical. Okay, lastly, as promised, there is a YouTube video. Now, this YouTube video is actually very long, so I'm going to encourage you to look it up on your own. But what it shows is a British gentleman by the name of Brian Cox going to visit the world's biggest vacuum chamber, which is actually a part of NASA where they test rockets and see if they will hold up under vacuum. For this, what they do is they take a bowling ball and feathers and they drop them. And the first drop, which is where we're going to start this video here, is with air resistance still in place.
And a light one, and drop them at the same time to see which fell fastest.
No big surprise there that the bowling ball landed before the feathers, because the feathers are going to have a much larger air resistance acting on them. If we now advance the video, you can see kind of they're closing the vacuum chamber, control room, control room, control room. Back up just a little bit. Okay, control room. You can see there's the trigger. That's going to cause the bowling ball and feathers to drop again. But air resistance has now been removed because they've pulled a vacuum. They've pulled all the air out of this large chamber.
Cameras on, 2, 1, release.
And quite nicely, with air resistance removed, you can watch the bowling ball and the feather fall perfectly in tandem with each other. This concludes this part of Unit 3.